if you remember in our GeoGebra examples, we looked at something similar to this. I hope it was exactly this, but I can't remember. And essentially, when we started looking at the sequence of partial sums, this was an example that diverged because my partial sums were going up like that, right? And we might ask ourselves why that is. And so if we look at this AN, right? AN, and this is not going to be like a super proof or anything, I'm just going to do sort of heuristically to understand. This AN here, n plus 1 over n plus 2, this guy is 1. Okay? So if I look at the partial sums, and I don't really want to write out too many of them, but the first one would be 2/3, and then the second one would be 2/3 plus 3/4. Okay, so after pretty closely, let's say 10, right? We keep going down. So the 10th is going to be 10/12, 11/12, right? So 11/12 is kind of small. It's kind of close to 1. And so if I get really bigger here, if I'm at S50, right, all the way here, I'm adding 51 over 52. 51 over 52 is pretty small, right? But, I mean, it's not as pretty small. It's pretty close to 1. The difference between this and 1 is small. So then when I look at 51, essentially I've got to the point where I'm basically adding 1 each time. So even though it might not be easy to write this Sn down in a closed form, which I don't want to do because I don't think you can do it very easily, but you can see what's going on here. At some point, I'm so close to 1 that I'm adding 1 each time. So my partial sum Sn is going to go off to infinity because each time I'm adding another 1, right? And then I'm just going to go off to infinity. So that's the idea here. And in fact, we can use this as a test for divergence. If the limit of this sequence isn't 0, something like this is going to happen. Even if the limit's something very small, I'm still going to be far enough when I'm close to that limit that I'm effectively adding that number again and again and again and again, and it's going to take it to infinity. So basically, what this is called, all right, actually let me do it slightly differently. We have a theorem which is related to this. If you have a convergent series, then it necessarily has to be the fact that the limit of the terms in the sequence has to be 0. Okay? This is not difficult to prove. It's in your book. It can be a little confusing, perhaps, but it's not hard. And you can very well see it if you think about the examples that we did. In order for the partial sums to go to a finite number, you have to be effectively adding very, very little at the end. You have to effectively be adding 0. So these terms have to go to 0. The really important thing here that you have to know so that it doesn't mess you up is that the converse of this is false. So, meaning that the limit of an equals 0 is not good enough to let you conclude that your AN converges. And our counterexample is precisely the harmonic series that we did in a previous video, right? 1 over n goes to 0, no problem, but once I start adding them up, it ends up growing without bound. So that's a really good one to remember to help you do this, okay? So in essence, this theorem only works one way. So the converse would be the limit of AN equals 0 implies that the sum converges. It's not true. What you can say is that the contrapositive is true, right? Because a statement and its contrapositive are logically equivalent. So the contrapositive of this is what we call the test for divergence. And it's what we did with our previous example of the n plus 1 over n plus 2, right? If my statement is if p then q, the contrapositive is if not p then not q. So if the limit as n goes to infinity of an is not 0, then the series, does not converge or it diverges. Okay? So this doesn't tell you all of the divergent sequences because as we saw, there's a lot of divergent sequences where this an is 0, but if you have limit of an not 0, then you know immediately that it diverges. So I'll just leave that there. That can be helpful with this section. But think about after this section, after 11.2, we're going to go through the rest of the chapter, and there's going to be all these different tests for convergence. How do you test this? How do you test that? The first thing you should always do is sort of look at that an and make sure an goes to 0, because you don't want to be spending a lot of time on something really complicated when it could be an easy one that you can recognize is not doing what you need to do.